going to be done after the AP test, but listen to this, because it's not going to look like it at first. Like when you turn the page and you see the crazy symbols that are on there, you're going to say, oh, what the heck? And in fact, I'll read you what it says, and you're going to say, what the heck? And then I'll explain it, and you'll still be confused, and then we'll do an example, and you'll still be confused. But then after you see it a couple more times, you'll be like, oh, this is actually easy. So please trust me, at the end of the year, after your AP test, I wouldn't choose something that's like super hard, super labor intensive. But you do have to pay attention a little bit. So watch this. Oh yeah, this first part, you can read it if you want to, but basically here's the summary, is that when you guys learned limits at the beginning of the year, or actually even before the beginning, like last year in pre-calculus, you guys learned them like, just look at the graph and see what it's approaching, like what's it getting close to, that's what a limit is. But that's very informal and imprecise and not rigorous. So today, here's the actual rigorous definition of a limit. But this also goes into like how Newton and Leibniz, the people that developed calculus like from scratch, they didn't actually use limits. They used something called infinitesimals, which were just like really, really, really tiny, infinitely small numbers. But it was like not super formal, not super rigorous. They would just say, see, it's so small that you can ignore it, but sometimes you can't. But sometimes you can ignore it, but sometimes you can't ignore it, but you can, but you can't. And so critics were like, I'm not sure about this calculus stuff. Like, I'm not sure how valid that is because it's not very rigorous and not very formal. And like hundreds of years later, Cauchy came up with the definition of a limit, and it made everything calculus like all click and make sense and be rigorously defined. That's what this says. Now, what does that have to do with you? Not much, but it's kind of interesting. What you guys have to know is the following. So watch this. Let me move this chair out of the way. All right, what you guys have to know is this definition of a limit, which again, I'm going to read it, you're going to get confused, and then I'll explain it, and you'll still be confused, but eventually you'll get it. Hey, Charlie. Hold on. Thanks. Wait, take this, if you will. Okay. So a limit, what you guys know as getting really, really close on the graph, what it actually is the following. Listen, you're not listening if you're whispering to your friend. Or I don't even know, your neighbor. You don't, I guess you don't have to be friends. But it says that a limit, well, let me just read it. We say that the limit of a function is L if for all epsilon greater than 0 there exists a delta greater than 0 such that if the distance between x and a is less than delta, then the distance between f of x and L is less than epsilon. Very, very confusing, a lot of abstract, crazy letters in there. But here's what it basically, well, okay, in oversimplified terms, it's talking about if you're really close to A on the x-axis, then you should be really close to L on the y-axis. That's why it's talking about distances. But more in detail, what it's actually saying is the following. You think that the limit of a function is L, but your worst enemy doesn't believe you. He says, prove it, or she says, prove it. And so your worst enemy, let me just pretend it's a he for the purposes of this illustration. Your worst enemy says, I don't believe you that that's really the limit, so you're going to have to prove it by, I'm going to choose a tiny interval that you have to stay within on the y-axis, and no matter what number you plug in from x, it should stay in that range on the y-axis. More on that to come, but that's the idea, so that will explain what I'm writing up here. So watch this. It says, for all epsilon greater than 0, there exists a delta greater than 0, means basically what I was saying. Someone will choose, your worst enemy, someone will, that'll try to make it really, really hard for you to prove, will choose a tiny number epsilon. Actually, let me see what I said on my key so that it's exactly how I want to say it. If you give me any tiny number epsilon, that says number, And again, this tiny number is like a range that you're allowed to stray from L, from your proposed limit. In fact, let me put that in parentheses. How far you're allowed to stray. Allowed to stray from L on y-axis. Oh shoot, if you give me that, comma, then I'll find a number on the x-axis so that if I stay within that range on the x-axis, I will stay within the range on the output axis. Let me write that down. If this happens, then, oh shoot, no extra comma, then I will be able to find a number delta so that, sorry, I know I'm in your way. Alright, you give me a tiny number to stay within on the y-axis. I will find a tiny number, well, not necessarily tiny, but most of the time it's tiny, so that on the x-axis, if I stay within that range, I will stay within your range on the y-axis. So that's what this part is saying. If the distance between x and a is less than delta, or in other words, any number within delta units of a, this a, or that a, on the x-axis has an output within epsilon units on the y-axis. We'll get out of your way. L on the y-axis. Okay, so again, we're talking about distances. That's kind of maybe all your understanding so far. At least if when I was a student, they told me this, and I had no idea what was going on. Then they drew me this picture, and I still didn't super understand, but hopefully I do it in a way that makes you kind of understand it. So watch this. In a picture, it's saying, I'm trying to leave that up there so I can refer to it. In my picture, they're saying you have some arbitrary function that looks like whatever, like that. This is f. And then and then you're interested in the limit at a for whatever reason. So let me put an a, and there's anywhere a right there. Okay. You guys just went through calculus and pre-calculus, and you know, just by looking at this graph, that the limit at that point is obviously this, the y value at that point. L. You know that, but again, your worst enemy doesn't believe you, and he says, prove it. Okay, so the way to prove it is, he's going to make it really hard. He's going to say, if that really is the limit, then you should be able to stay, people in the video can't see, but you can kind of make, understand that I'm making a tiny range around L, and your worst enemy is saying, okay, find a range around A so that no matter what you plug in that range, that stays within my fingers of L. That's how you prove to him that that really is the limit. Tiny distances on the x-axis correspond to tiny distances on the y-axis. Okay, so in a picture, let me make it a different color. In a picture, again, the idea is that epsilon is tiny, but pretend this is really zoomed in just for illustration purposes. Oh shoot, that's not epsilon, but the distance. The distance between your L and the range that your enemy gave you, that's epsilon. So what I mean is, this is epsilon, and this is epsilon. You can stray up or down from L epsilon units, but you have to stay within there. That's the epsilon that your enemy is choosing. And then your job is to find a delta so that you can stay within it on the x-axis. So I guess in this case it would look something like, that would be your delta anything within this range would be within delta units of A. Like this is what you choose your delta to be. Let me do it in purple. This is the delta. How far you're allowed to go away from A. So one more time, and even if you don't get it, you don't have to freak out. Like you'll see that the problems, the procedure is really easy. But one more time, basically, you found this range right here in purple, and you can see, choose any of these numbers and plug them in. Oh, you're within the red range that your enemy gave you. That's what the definition of a limit is saying. Okay, yeah, question.
On the spot where it hits the f of x twice, would that still count?
I guess, not really. I'm kind of,
because that would give
actually,
you the
I
same
mean,
limit of within the range.
but not all the way over here. Allie, for the people in the video, somebody's asking about, don't write this, anybody, but if I had chosen this to be delta, like that huge delta from here all the way to here, then you can see there's one spot like right here that's not within the red range, so you would, that's why you wouldn't want that as a delta. Like you want the closest one, basically. All right, let me undo all that. So before people get confused, get out of here, get out of here. All right, other questions? Again, you don't have to be super concerned if you don't get it right now. Okay, cool. Okay, so why don't you have to be super concerned? It's because, watch this, the problems that I'm giving you for this time in the year after your AP test with low motivation and 5 weeks left of school are all going to be just like linear ones, which are really, really easy. If you see this, okay, I forgot to say this at the beginning of the year, but the reason I thought this was kind of worthwhile is because for sure you would have seen it in calculus, like in college. And in fact, even if you get the AP credit and you skip Calculus 1 or whatever they call it, in Calculus 2, at least when I went to college, they had me learn this. So at least you get a sneak preview. And when you go to college, either they'll just give you the easy ones, or maybe they give you like some tricky ones with quadratics, but at least having the foundation of having done these easy ones hopefully makes it easier in college when you get them. But anyway, here, let me make a little divider between problem 1 and 2, because I'm going to be writing a good amount. But all it's asking you is, of course, you guys know that the limit of this function at 5 is 17, because you just plug in 5 and you get 17. But the proof doesn't go, oh, just plug in 5 and you get 17. The proof has to show that this limit follows the definition. So what you have to do is say, okay, here's what I want. I want this to follow the definition, which says that any number really close to 5 should have an output really close to 17. In other words, if x minus 5, that distance is less than whatever delta I pick, then I would like the output 3x plus 2 to be really close to 17. In other words, 3x plus 2 minus 17 should be less than the epsilon that my worst enemy is choosing. Okay, again, don't freak out yet, because these are really, really, so you're trying to figure out what delta am I going to choose, because he has the freedom, my worst enemy has the freedom of choosing any epsilon in the world. So how am I going to choose a delta just in general? Well, again, don't freak out yet, because these are really, really easy, at least for linear functions, because watch this, 2 minus 17, this will always happen that you get some sort of simplification like this. 2 minus 17 minus 15. Then it's always going to be true that you're going to be able to factor out that 3 in front, or whatever number is in front of that. So you get 3 times x minus 5 in here, less than epsilon. And then this x minus 5 will be good news for later. But more on that to come in a second. Something else that's like, seems elementary but it's not super obvious is that the absolute value of 3 times x minus 5 is the same thing as the absolute value of 3 times the absolute value of x minus 5. So this will be helpful if you write this. Oh shoot. Or if you haven't even written that yet, then you might as well take off the absolute values from the 3, because the absolute value of 3 is 3. So basically, you're factoring out a 3 out of the whole absolute values. So it looks like this. 3 times that. And then last step, watch this, is if I divide by 3 on both sides. Then look what you just got. Look what you just got. You were like, oh, I wish I could find some number delta so that if I have x minus 5 is less than that number, then I get this, what I'm highlighting right now, automatically as the result. And we did some algebra and we got, oh look, if x minus 5 is less than epsilon over 3, then I automatically get that result up there just by doing some algebra. Meaning, again, if you don't get it, don't freak out. The idea is basically that for whatever epsilon your worst enemy chose, that's going to be your delta, and that'll guarantee your definition fits. Hey, Adam. Wait, Adam, here. Enjoy. Okay. So now you've done it. You just have to like write it out in a way that your worst enemy cannot refute that that really is the limit. And so you do it like this. You say let epsilon greater than 0. Let epsilon, let this positive number epsilon be chosen by you, my worst enemy. So let epsilon greater than 0 be given. Now, no matter what you chose, I'm just going to take that epsilon and divide it by 3. And that should give me the definition that I wanted. So I'm going to say set delta equal to epsilon over 3. This way, if, and then remember, in the definition, I'll let you catch up for a sec, but then I'm going back to the definition really quick. Okay, watch this. In the definition it says, if this is true, x minus a is less than delta, then the function output should be less within, should be within epsilon. So in other words, if I choose delta to be this, then if this happens, x minus 5 is less than delta, I'm just grabbing this straight from the definition, then this will be true, what I'm circling with my mouse right now for the people in the video. Then, watch this. Actually, I don't need that little arrow yet. Okay, if x minus 5 is less than delta, then we just agreed delta should be epsilon over 3, so let me just replace that. X minus 5 is less than epsilon over 3. And then watch this, if I just follow this backwards, then I get to the exact result that I want. So now if I multiply by 3 on both sides, boom, that inequality implies that this inequality is true. Multiplying by 3 on both sides. Then, boom, I distribute that 3 and I get the following. 3x minus 15 is less than epsilon. And then just slightly rewriting minus 15 as plus 2 minus 17 gives me the result that I want. And then you rejoice because you did it. You showed that if this happens, if any number is within delta units of 5, then the output will be within epsilon units of the function, or of your limit. So you kind of did it. You could stop there, or you can make it like super clear. Therefore, the limit as x goes to 5 of the function 3x plus 2 really is 17. Boom. And now your enemy can't refute you. Okay, so depending on the level of understanding you're looking for, you might have questions. But if you're just looking for how do I get the points on Tuesday, then you follow these steps every time. And this epsilon over 3, it's not a coincidence that that 3 is that 3 right there. That's always going to be that. So divide the epsilon by whatever coefficient is in front of your function, and that'll get you your points. And you can always follow this little template. So let me do one more just so you see it, but I don't have to explain every single thing so we can move faster, and you'll see that it's not that hard. Okay, watch this. So again, the setup is the same. I want that if x minus 2 is less than delta, then that should imply that the outputs are within epsilon of 5, so like that. Okay, then like I said, this is always going to happen. The plus 1 minus 5 will simplify nicely. In fact, so nicely that you can always factor out that 2 or whatever's in front of your function. And then this x minus 2 should match the x minus 2 that you started with. So if I just divide by 2 on both sides, then now I see, oh, this should be my delta. Because the inequality that I just ended up with will guarantee that the first inequality, the original inequality, is true. So in other words, now I'm just following the template that I wrote up there. Let epsilon be chosen or be given. Now, okay, you, my worst enemy, chose that epsilon. No matter what you chose, I'm going to divide that by 2, and you'll see that that works. So I say set delta equal to epsilon over 2. That way, if x minus 2 is less than delta, then that means that x minus 2 is less than epsilon over 2 because of what I chose delta to be. Yeah, and then now I just follow this backwards, boop, 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 multiply by 2, and that gives me this inequality is true. Distribute the 2, and that gives me 2x minus 4 is less than epsilon. And then rewrite the minus 4 as 2x plus 1 minus 5 is less than epsilon. Boom, end of proof if you want, or you could make it even clearer by saying thus by definition, or whatever I set up here. Therefore, this limit is true, but I already committed to this. Thus, by definition, limit as x goes to 2 of 2x plus 1 is 5. Okay. Cool. I mean, that's what I did with my other 2 classes, and then I stopped. Because this number 3, number 4, all of them are the same thing. So if you can just follow those steps, then you're good for your 8 points on Tuesday. If you want more deeper explanation of what's actually happening, then I'm here to answer your questions. But if you're just trying to get your 8 points, that's kind of all you need to know. Let me say a couple things. Again, I'm skipping this, I'm skipping that one, because I think you get the point. Remember how I said I copied this from previous years? I think last year when I taught this, it was like senior skip day, and so I did want to teach it because we had just spent a week chilling, but I didn't want to punish all the people who skipped. So I made it 8 bonus points, but this year that's not the case. Sorry, just 8 normal points. Sorry. And then the other thing I was going to say is I'm just going to check, don't turn these in on Tuesday, I'm just going to check them. So you'll come in tomorrow, you'll do these 2 problems, and then I'll check everybody and give you your points right then and there, so that I don't have to grade anything later. Which means if you do them right now and show them to me today, then you don't have anything to do tomorrow, and you can hang out. My Switch is still here, my guitar is still here, and you can hang out. So, okay, up to you. I'm also here for questions today. I'm here for questions tomorrow. But that's what you can expect for the rest of the year, is these little short, easy lessons, hopefully. Thanks, y'all, for listening.